Hello everyone, this is Jack Hassamon. In this lecture, I will talk about how we study manufacturing process and how we select one process over another for a product. As you may know, there are so many manufacturing processes that we could possibly study and perhaps imagine. And in each process, there are some variations on toolings. Our study could be endless. So we do need to create some kind of structure in our study so that we don't get lost. I recommend you to first watch this video on YouTube. It will give you a good idea how we classify manufacturing processes and how engineers choose a manufacturing process for a product. Obviously, cost is a critical element in our decision making. Designing a product, selecting materials, and manufacturing processes for each component within the product requires some knowledge to make good decisions. We will not talk about product design at this point. Let us start with how we select materials for a product. Engineers will likely start with forms and functions. How does a product look? How is it used? This will determine mechanical or physical properties of material we use. These mechanical and physical properties are what we have already known. If our product needs to undergo large forces, we need to make sure it has good yield strength. Should it be rubbing against other components, we need to specify surface hardness. Is it used in high temperature environment? Is it used in high moisture air? Should it be shiny or should it absorb light? Should it be lightweight? Engineers need to specify these properties as detailed as possible so that the right or the best material is selected for the product. And there are plenty of tables like this to help us select material which can be metallic or non-metallic. This table is for yield strength. This table is for basic physical properties. Density is specified when the weight of the product is our concern. Melting point is specified when our product must be in high temperature environment. Specific heat is the amount of heat that is used to raise 1 kilogram material by 1 degree Kelvin. And we use specific heat when we need to heat our product regularly, such as kettle that we use to boil water. Thermal conductivity is very similar to specific heat. It is the amount of power needed to raise the temperature of material 1 meter away from the heating source by 1 degree Celsius or 1 degree Kelvin. Thermal expansion coefficient is how much 1 meter length of material is expanded when the temperature is raised by 1 degree Celsius. Next issue we need to consider when we select material is manufacturing properties of that material. Some manufacturing process is well suited for some material. This table shows that which material has been used with which process. Dark bullet means the material has been used frequently with the process. White bullet means the material has been used sometimes with the process. A dash means that the material has never been used with the process. For example, if we look at the table under the column stainless steel, we will see that it has been used frequently for metal spinning, swaging, tube bending, roll forming, and forging. It has been used sometimes for extrusion, stamping, powder metallurgy, and screw machining. It has never been used in impact environment. And this is the whole table shown in the textbook. Indeed, we have many more manufacturing processes and many more materials than what are shown in the table. This table only serves as a starting reference that some material is well suited for some manufacturing process. Given a material, there are only some manufacturing processes that we can use. At this point, let us not worry about manufacturing processes that are mentioned here. We will discuss some of them in other lectures. Another aspect we need to consider when we select material for our product is how can we buy this material? What should our starting raw material look like? Can we buy this easily in the market? Are there many raw material suppliers in the market? Some materials are already available, meaning it can be bought easily in the market in many shapes, such as plate, sheet, foil, bar, cube, wire, structural shapes like T-bar, I-beams. Some are sold in rectangular or circular beam known as ingot or billets. Obviously, one of the key considerations when selecting a material is cost. Material cost is the main component in any product. Perhaps for convenient purposes, most materials are sold per weight. For example, steel bar costs around 15 to 16 baht per kilogram. Now, let us move on to see how we select manufacturing process for our product. The very first thing to consider is whether process can create or make the product to our specification. We call this process capabilities. Process capabilities in our discussion here refers to geometric features, shapes, or sizes of the final product. As we study more manufacturing processes, we will know intuitively which process can create certain geometric features. For example, if you want to make that flat surface, we can consider rolling, planing, broaching, milling, shaping, and grinding. To select which material fits the best for our product, we need to look at overall product shapes and sizes. This is the whole table from the textbook again. This does not include all manufacturing processes that we know of, nor does it include all geometric features that we possibly need. Process capabilities can go deeper to consider whether the manufacturing process that we select can meet designers' specifications, such as dimensional tolerance and surface finish. Each process has its own tolerance and surface finish range. Machine tool manufacturers also constantly improve process capabilities. So these diagrams are just rough guidelines for us to see which process is potentially or particularly good for dimensional tolerance, which process is good for surface finish. The second aspect we need to consider when selecting a manufacturing process is its influence on properties. Some process needs to melt material to liquid. Some process needs to heat material to soften state. In some way, manufacturing process has some effects on physical properties of the material. For example, some forming process affect material grain formation, leading to changes in material yield strength. The next aspect to consider is required production volume or rate. This determines the level of automation required for our manufacturing processes. When we need to make a few pieces of product for experimentation or to make prototype, we may need to use level 1, which is manual operation or basic machine tool. These are manual lathe and milling machines in our machine shop. As our lot size increases, we will need level 2 general purpose machine tool, which has many standardized toolings. For example, a turning machine with multiple turrets or spindle heads, a milling machine with multiple spindles. When we start to make products as many as we can, we will need level 3 and 4, which are special purpose machines, and connect them to create automatic production line. In the graph, you can see that as we increase lot sizes or production rate, shown on x-axis, we need to increase level of automation from 1 to 4. Note that y-axis, which is cost per piece, will decrease, as we increase lot sizes or production rate. Level 5 and 6 in the graph are to show that we have computer-controlled machineries that are capable to make small lot production to mass production. I would say these level 5 and 6 are not available to all industries. Most likely when we start select manufacturing process, we need to think about production volume requirements simultaneously. So we pick the process that can do the job. Again, we select manufacturing process also based on cost. Some companies select manufacturing process based on which machines they already have in their factories, so that they don't need to buy machine tools. Process costs that we are talking about are mainly machine and tooling costs. This tooling includes mold and die that must be specific to components or products. The table here only shows a rough guide how each machine costs compared to others. It can no longer be used for exact costing. It is very important to control manufacturing costs if we need to spend a lot of time and effort to make a product. Our manufacturing costs will go up because we need to spend our precious machining time on the product, and we need to hire human operators to work on the product. As a guideline, the design should be as simple as possible to manufacture. Materials should be chosen for their appropriate manufacturing characteristics. Dimensional accuracy and surface finish specified should be as broad as permissible. In this class, we will learn about some manufacturing processes. You will see very quickly that we cannot spend our time to study just one process in complete details either. Every process or machine evolves constantly. What we learn today can be outdated tomorrow. The purpose of this class is not to introduce you to as many manufacturing processes as we can. In my view, we will pick a few manufacturing processes and go deep in 4 aspects: what, how, why, and what can go wrong. Then, we will look into some variations around that process. We will see how this is done when we study manufacturing process from the next lecture onward. For now, just remember this: when we study a manufacturing process, we should simply ask what, how, why, and what can go wrong. What means how raw material is changed to final product. So we need a picture or diagram or some kind of illustration to show how raw material is converted to the final product. What is the shape of raw material that goes in, and what is the shape of the raw material that comes out? How does the process work? What does the machine look like? What are the tooling, jig, fixtures, mold, die required for the product? What does the machine or tooling do to make the process work? Why does it work? What settings are important to make the process work? What process parameters such as speed, distance, force are critical to the process? Are there any mathematical relationship among these process parameters? This why topic is probably the most difficult part. This is where researchers and machine tool manufacturers study the most. What can go wrong is a question manufacturing engineers should ask very often. We would like to think that our manufacturing process is under control, but this is not necessarily true. Our tooling gets worn out, and even electrical shock to the machine can affect its functionalities. Human operators may not set up the machine and tooling properly. Some nuts and bolts get loosened. Also, our raw material may be defective. As an engineer, we need to understand the cause and effect relationship. In this class, we will specifically use a tool called failure mode and effect analysis, or FMEA. To do FMEA, we start with picture or diagram of the process. We list raw material, and each critical components of the tooling and machine tool. Then we ask 3 questions. What is this raw material or component supposed to do? What can make it fail? What happens if it fails? We try to go as exhaustive as we can in order to identify critical raw material specifications, components specification, process settings, and parameters. We will have a chance to practice this in every lecture on manufacturing process. So here it is, our second lecture. If you have any question, please feel free to leave them in Google Classroom or keep them to ask me in our Zoom class. Thank you and have a good day.